Okay, let me just repeat what I said for those at home. Last time we studied the dependence on the amplitude on overall energy scales. So if we had any, say, Mandelstam, any momentum or energy, we just scaled every factor. And then explaining elasticity of the amplitude, you should make a very complex Z. And then by studying the dependence on the amplitude on this, we could do things like RG running, which was just picking up the discontinuities across the cuts, picking up the coefficients of logarithms in the EFT. And also what we call EFT matching, which is picking up the singularities which are in the UV theory, but which are missing at low energies. Okay, and this let us compute the difference between UV and IR Wilson coefficients. Okay, so we are still in this setup where we are thinking about the amplitude as some low energy expansion in inverse powers of the UV scale, where each one of these things depends on a bunch of couplings that, thanks to the running, we saw that they also depend on this UV. Okay, and so far, everything we could say about these coefficients is that we can compare them between different theories. We can extract the difference, but we weren't able to say anything about them, right? These are parameters in my theory that in principle I just have to go out there. But there's a question of, well, these principles that we've been discussing, unitarity, analyticity, et cetera, they're pretty constraining. So one can ask the question, is actually any value of these GIs allowed? So these GIs are some dimensionless Wilson coefficients, right? We're rescaling everything by this UV scale. So the question I want to ask today is any value of these GIs allowed? So, okay, what do you think the answer is? No? But do you think that before I ask this question? Yeah, so actually we'll see that at least the relevant couplings, they're actually constraints. So there's technical reasons why it's only the irrelevant couplings. Not every one of these coefficients is allowed, okay? Okay, so the answer will be no. What is the typical statement that we make with the coefficients? If someone asks you, what's the value of this thing, like generically, what would you say? Order one, yeah. So that we call usually conventional dimensional analysis. So this is that we say that these GIs are order one. There's a more refined version of this. Actually, this more refined version is called naive dimensional analysis. Which I always found a bit weird, because if this is naive dimensional analysis, this should be called super naive dimensional analysis, because this is a bit more precise. But never mind the name. So what's the statement here? The statement here is that, OK, we know that these coefficients typically run. So we know that if we study one of these couplings at some scale p star, then this will go like G at lambda UV. And maybe there's some one-loop correction. And typically, there's some powers of 4 pi in the denominator here, just coming from the loop integral. So for this to be consistent, we ask how big can this be? So maybe the theory is strongly coupled, so that the loop corrections are as big as the tree. So where does it actually sort of break down? We see that in this case, it should be when this G is actually some power of 4 pi. In general, any coupling, we expect that kind of the maximum value has to be some power of 4 pi fixed by such argument. So there's also some fancy way of doing this with a Lagrangian, which you can read in various papers. Now, where does this come from? Where does this expectation that these coefficients are small come from? It's based on experience, right? What I mean by that, let's look at an example. So let's look at an example where we integrate out some particle at tree level. Right? So what do we mean by that? Okay, integrating out, as we said, is just power series expanding. Right? So we have some propagator of this particle, and then we expand it for small values of p compared to m. And this thing is going to go like 1 over m squared, and then some infinite sum of 1 times p squared over m squared to the n. Right? So now each one of these powers will be able to write some term in the EFT, but you see that the coefficient here is order 1. Okay. Let me write another example. Same thing at loop level. Here we have something like log of p squared minus 4m squared. And for values of p much less than m, this is going to be like squared, and then a similar sum, but with a 1 over n. Sorry if you cannot see here, but it's 1 over n, and then p squared over 4m squared to the power n. So we see that, okay, integrating things out at tree level gives large coefficients. If we're integrating things out at one loop, it's suppressed by a 1 over n. Of course, this would also be suppressed by some coupling in the UV theory, so it might be even smaller than that. Yes?
So will it be a problem that this other series doesn't converge for very low or only modestly high momentum?
So this converges, like the radius of convergence is fixed precisely of when you see these new particles appear, right? So essentially, like what is this, right? This is some pole, right? So if there's some width, you would see some bump in your cross section, right? The EFT is just going to describe this part here. But if you get too close to the location of the new particle, then it's going to diverge. Yeah. So we only trust this for p squared much smaller than m squared. So in the EFT, m squared would be this lambda UV, or lambda UV squared. Did I answer a question, or did I misunderstand? Okay. Okay, so can we do better? And it seems that to do better, we need to know something about the UV, right? Because one way of thinking about these Wilson coefficients is they just parameterize the space of UV theories that at low energies correspond to our effective theory. Okay, so in principle, there could be something really crazy up there, and at long distances, we don't really see it, but it's encoded in pattern in these Wilson coefficients, so there's many options. So it seems that we need to know something. But I'll argue that the only thing that we need to know about the UV to put some constraint on its coefficients is, again, that it satisfies all of these principles that I'm talking about. Actually, I won't even use locality. So I'll argue that if the UV theory is causal, has some symmetry properties, and is unitary, then we're going to put some bounds on these G's. So there's two ways of doing this. This sort of program, sometimes it's called the S-matrix bootstrap. And though there's been something like that around for more than 60 years. Right, so there's two approaches. The first one is for a generic couple theory. Then it's very hard to say amplitude. As that we can do is we can make some ansatz numerically. So we can just write our amplitude as some sum over some space of functions. And if it is a good enough space of functions, which in principle is that can capture things like which have the same analytic properties of the amplitude, try to impose all of the constraints from unitarity, causality, et cetera, because we could try to impose that the imaginary part of this amplitude is positive, as is dictated by the optical theorem in the limit. And it's brute force, like you have to be very smart to choose the space of function. You have to be very good at numerics, and then you can just put this into a computer, find a function that satisfies all of the axioms, and then expand the energies and see if you can find a function that has the minimum value or maximum value of one of these Wilson coefficients. Okay, so this is some numerical approach. So find AIs such that all axioms are satisfied, and then minimize or maximize one of these couplings at low energies. Okay. Now, I cannot do this on the blackboard, so I'm not going to discuss this today, but this is something that has been very successful in the last few years. Yes?
What is the sum?
What is the what?
What is the sum?
This sum? Yeah, you can think of this as writing the amplitude a basis of functions, unknown coefficients.
What is I denoted?
I is a label for each function in the space, right? In each element of the spaces.
The coefficients are the function of couplings?
The coefficients are just numerical coefficients. Like here, I'm not writing the amplitude in terms of any couplings. This is really just some number, right? Now, if I expand this sum at low energies, of course, I can write EFT couplings in terms of these guys, and in terms of coefficients that come from expanding these functions. And I could try to minimize or maximize one of those. Okay. So people have applied this to effective theory for gravity, for pions, for thinking about the QCD string. So there's a whole research program which has been very popular and has found some success in the last 5 or 6 years playing this game. There was a question?
Is there like a specific case of function that we could?
So that's the hardest question. And oh yes, the question is there? Sorry, I didn't repeat any of the questions. The last question was, is there a specific space of functions that? So yeah, what people do, for instance, is they try to find a space of functions that themselves have the sort of branch cuts that we expect in the amplitude, that have some like square root type branch cut. For instance, like okay, if we study the function in the S-plane, we'll discuss this in more detail, but we expect that there's some branch cut starting at some mass. Another one here, maybe some poles. So people choose functions that they're basically analytic like everywhere except for here where they have some type of squared branch cut, and the hope is that by doing an infinite sum of this, you would be able to reproduce any actual, at least numerically, the behavior of an actual amplitude there. Okay, but this is a very hard. And for instance, people have only been able to do this at 4 points. Recently, some progress at higher points, precisely because we don't understand the analytic structure of the amplitude well enough to find a good space of functions. Okay. What is the other approach, which is what I'll be talking about? We need to make some assumption of recoupling. So the assumption, so this is the version I'll be describing, which is the assumption would be that the leading irrelevant coefficient, so the leading Wilson coefficient appears suppressed by multiplied by the right power of lambda. So actually, sorry, in my language, this is already dimensionless. So as long as the leading Wilson coefficient is small, then we'll make some statement. Okay, so this will lead to directly these bounds on these ratios. So we'll be able to put bounds that look like this of any other Wilson coefficient, other irrelevant in leading one. Okay, so let's do this. So let's start again by listing all of my favorite principles that we're going to use. So we're going to use causality, which, remember, was analyticity and crossing. We're going to use some version of locality. So which version? We're just going to study the amplitude as a function of the center of mass energy, the Mandelstam S. So we'll look at 4-point amplitudes, right? So this amplitude is a function of S and T. So now instead of looking at how the amplitude depends on varying all of the Mandelstams at once, like last time we were studying the dependence of the amplitude at fixed angle. Now we're going to do it at fixed T. So at fixed momentum transfer, we're going to study the dependence on the amplitude on the center of mass energy S. So what does this look like? Okay, so there can be some poles here at low energies. Maybe there's some branch cuts starting at some UV scale. So for us, this generically would be kind of the mass of the first particle, which is not in the effective theory. On the other side, there's going to be also some branch cut at minus T minus lambda UV squared by crossing symmetry. So crossing symmetry tells us that the amplitude makes sense for any complex value of S. If we look at the amplitude here, it's looking at particle 1 and 2 scattering into 3 and 4. If we look at the amplitude here, this will be the complex conjugate of 1, 3 bar scattering into 2 bar 3. Okay, and yes. Okay, so we just understand the dependence of the amplitude on S, and then we need a couple more things. So instead of using unitarity to fix the coefficients of these kind of logarithms, because now these branch cuts live at high energies, then we can say much less about it. So what does symmetry tell us? Okay, so the minimal assumption that we can make is use rotational invariance at high energies. So, oh, yes.
Sorry, maybe you mentioned it, but why is like one of the poles minus t minus uv squared and the other one is just uv squared?
Yeah, so the question is, why is one of the poles here and the other ones are is at minus t minus lambda uv squared, right? So this thing here, this would be something like 4 times mass of the first new particle. If it was a pole, then it would be just the mass of the first new particle, right? So in the EFT, if it was a pole, it's because it's breaking down precisely when you see this pole, which is not seen in the EFT. If it's a log, then it would be a bit further up, but that's the origin. So this is, in this case, S, right? But then crossing symmetry tells you that on this side, there also has to be such pole at u minus m squared, right? And if you write this in terms of S and T, you will find that it's here. Yeah. Okay, so we're just going to use, are there any more questions? We're just going to use basically rotational invariance. And we're going to say, okay, what does rotational invariance tell us? We can just expand the amplitude in some basis of partial waves, right? So the 4-point amplitude is going to look like 16 pi, sum over spins, 2j plus 1, some partial wave coefficient that depends on S, and something like a Legendre polynomial, or if there are particles with spin, this would be some Wigner-D function or something like that, which depends on the angle. And this angle, in terms of S and T for massless particles, is just 1 over 2T over S. Okay, so rotational invariance tells us that the amplitude can be expanded in a basis of known functions. So these guys we know. And all of the information is encoded in these partial wave coefficients, which are unknown a priori, especially at high energies. So we might know what these things are for S much less than the cutoff, but for S above the cutoff, we don't know what these AJs are. But we know something about them, thanks to unitarity. So what does unitarity tell us? Always that the imaginary part of the amplitude is positive, right? Like the optical theorem, right, tells us that S dagger S equals 1, right? And if you write S as 1 plus IT, where T is the amplitude, let me just call it A, then what we learn is that the imaginary part of A goes basically like A squared, and it's positive. So how is this encoded in this situation? Well, it turns out that typically to apply the optical theorem, we need to introduce a complete set of states, but it turns out that the partial wave transform trivializes that integral. So two-particle phase space integral is kind of diagonalized by doing the partial wave expansion. So unitarity takes this very simple form. I'm sure you've worked out in your quantum mechanics class. I saw you, 1 second. That looks like this. Imaginary part of these AJs goes itself as AJ squared, so it's positive. Yes?
I was just wondering what the subscript on the A is there.
Here, it's J. It's this.
On the left side, capital A there.
Oh, capital A. Ah, it's a 4-point amplitude. Yeah. Okay, so it seems that we don't know what these A's are, but we know something about them. We know that their imaginary part is positive. Right? How should we think about these A's and about this imaginary part? Right? So if you think, for instance, about the scattering of some particle that has spin J and some mass M, then if you compute this sort of Feynman diagram, you will see that this thing goes like, okay, I have some coupling here, have some, we call it lambda. So this will go like lambda squared S minus m squared, and precisely the spin j Legendre polynomial. Okay. So when we take the imaginary part just comes from the I epsilon in this pole, so the imaginary part is just this coefficient here. Okay, so in this case, imaginary part of this partial wave would just be this lambda squared, which tells me how my particles couple to this kind of heavier spin j states. Okay, so you can think of this imaginary part of A as telling us how do my particles that I'm scattering in the S channel couple to some heavy state in the spectrum that has spin j. So it's just the square of its coupling, so that's why intuitively it makes sense that it's positive. Okay. This is an example. It could come from loops. It could be more complicated, but at least for intuition, it's always something like this. Okay, there's also something else. The unitarity tells you that this imaginary part has to be also less than 1. That has to do with the fact that cross-sections have to be less than 4 pi. But actually, we won't use that. We are just going to use the positivity.
Sorry, that would be an upper bound.
That would be an upper bound, yeah.
Why are you using?
Because I don't have to. So it's actually, no, the actual reason is because of this assumption. So the fact that I'm assuming that I have some form of weak coupling means that by assumption, my cross-section won't ever be too large. So actually, there's no like actual way to get anything interesting from that upper bound. Whereas in this approach, people definitely impose that upper bound. Positivity will be enough. That's what I meant by I don't have to. So just from the positivity of the partial waves that comes from unitarity, I'll be able to say something about the Wilson coefficients. Okay, and the last thing I need, so I'm just giving all the ingredients I will put together in a second. It's something that's slightly technical, but I want to discuss it at least for a couple minutes because it's important. So when you put these principles together, actually they imply something else, which is that if you take the limit when the absolute value of S goes to infinity of the amplitude at fixed t, right? So this is kind of a high energy limit for real values of S, but here I'm also going somewhere else in the complex plane. So for real value of S, this is called the Regge limit. The amplitude has to go slower than S squared. Okay, so if t is fixed, so this tells you that the amplitude cannot be too badly behaved at high energies, even somewhere off in the complex plane. This is actually very hard to prove. Only recently people were able to make some progress at actually explaining why this is true. But there's a toy model that we can use to understand why something like this might follow from the principles. This is something called, sometimes called a signal model. So let's just study, we have some wave packet which is outgoing, which depends on t, and this comes from integrating some kernel, which is kind of my avatar for the S matrix. And there's some initial wave packet. Okay, so in Fourier space, this looks much simpler. It's just multiplicative. So this is a one-dimensional problem. I have time. It's like something like scattering in quantum mechanics. I'm just looking at dependence on the energy. And unitarity tells me that the absolute, so say this is normalized to be 1, right? The initial wave packet, the norm is 1. Okay, the the final wave packet, it has to be less than 1, right? Because there could be different states that this can end up on. So unitarity tells us that the absolute value of this thing needs to be less than or equal to 1 for real values of omega, for actual physical energies. And actually, if we assume this thing is sub-exponential, meaning it doesn't grow exponentially somewhere, so if I now take omega to be large in the complex plane, on the real axis we know it's bounded. If I assume that it grows slower than exponential, there's a version of the maximum principle, right? In complex analysis, you have that if you have a function, some analytic function in some bounded region, it always takes its maximum value on the boundary, right? There's something similar when you have something like the upper half plane, right? So remember, we discussed that causal observables are well defined for frequencies which live in the upper half plane. So this thing is called the Fragment-Lindelof principle. Whatever the statement is that this is actually true in the whole upper half plane. So meaning if the imaginary part of omega is less than or equal to 0. Okay, so this is some complex analysis mumbo jumbo, but the point is that we'll see that actually this implies that there's a bound on how big the amplitude can be.
Less than or equal to 0 or greater than?
Greater than or equal to 0, because that is the upper half plane, so positive imaginary part. Okay, so if we choose this thing to be, as usual, 1 plus IT, and let me take t to have this following simple form. T0 s to the n. The statement that this thing is bounded by 1, again, is the same as the imaginary part of this thing being positive. So the imaginary part of this t omega, you can calculate it. It's going to be something like T0 absolute value of omega to the n sine of n theta. So I'm choosing s to omega to be, whoops, I'm getting mixed up. So here is omega in the end. I'll say something about s. So this is just the frequency. So I'm choosing the frequency to be e to the I theta. This is the argument. So the imaginary part is something like this. And if this has to be positive, that can only be true. So theta goes, right? So if n is greater than 1, this is going to switch sign somewhere between 0 and pi. Okay? Only if n equals 1 or less, this thing can remain positive in the whole upper half plane. Okay? So this implies that n has to be less than or equal to 1. You see that causality, unitarity, analyticity imply that something like an S matrix cannot go arbitrarily fast at high energies. Okay, so this is a technical point. So if this is in the toy model, then you might believe that it's true also for a more complicated case of the amplitude. The whole point is that we're going to use this now in combination with the other principles to write a dispersion relation we will use to put these bounds on the Wilson coefficients. So dispersion relation is always one of these fancy contour integrals in the complex plane. So we're going to ignore, because of this weak coupling assumption, we're going to ignore loops and all of that, at least at low energies, and we're going to think about what happens with the amplitude. So let's consider the following contour integral. So remember, my complex plane looks something like this. Maybe I have some poles at low energies in the EFT. This is lambda UV squared. Maybe here I have some branch cuts that come from the high energy stuff, right? So this is the S plane at fixed T. And let me write the following contour integral. S prime, S minus S prime, A S prime T, okay. This might seem a bit mysterious. So this S prime, I can just put this pole somewhere here, right? So this is S prime equals S. Actually, let me write it the other way around. And here I'm computing precisely the residue at this point. Okay. So this thing is just a weird way of writing the amplitude. Because this, if I just compute the residue here, this just gives me back A of ST divided by S plus T, which is SU. So SU is the thing that gets swapped under crossing. Okay, why did I divide by this factor? Because now I can take this and do the usual trick, use Cauchy's theorem. I'm going to deform this contour, right? I'm going to unfold it. So what does this look like? Let me draw it here. I'm going to write an example in a minute, so don't worry. Almost there. So when I unfold the contour, this thing is going to pick up kind of residues at low energies. So there will be some circle here around low energies, which will pick up the poles in the EFT. There will be some integral across the branch cut. And then there will be an arc at infinity. Right? And here we had our original pole that now we are not surrounding. But I just told you that the amplitude cannot grow faster than S squared at infinity. And since I divided by S squared, that means that actually this arc at infinity will always give 0. Okay? So this was something which we needed to figure out. There's this technical thing, which is the amplitude grows at infinity, but it's important because it means that we can actually forget about this. So what does that mean? That means that we can write the amplitude so this is what we get when we evaluate the integral by just computing the residue here. But then we can also evaluate it here. So the amplitude will be something like so it will be the contribution from the residues in the EFT. So this is something that we can compute in the effective theory. It's this little circle here. So we're just picking up whatever is there in the EFT. But more importantly, so this is, let me call this 1. So this contribution is 1. But then there's something like the integral from the UV cutoff to infinity of the difference between the amplitude here and here, but that's precisely the imaginary part of the amplitude, right? This is S plus I epsilon over S minus I epsilon. So it's a discontinuity across this branch cut, which is just the imaginary part of the amplitude. So this is going to be So let me write it now S as m squared, just to be suggestive. Yes.
So here you really rely on the fact that it's a strict equation.
Yes.
Because the argument that was shown.
Yeah, this was a toy example. This was a toy example. This is not the same as that. But yeah, you need it to be strictly.
There is also ways to convince us that it should be strict or like I don't know.
Yes, not in half an hour, but yes. I can explain later. Yeah. The question was whether we need the strict inequality there for this dispersion relation to be good, and the answer is yes. And I didn't show that. I just showed some toy example which actually doesn't satisfy the strict inequality. Okay, so there's this thing here, and then m squared minus s, the imaginary part of the amplitude. And then there's also a contribution from this cut, which is the same thing when s u. So minus s minus t. Okay. Now, why is this good? Because we know something about this. I just erased it, but I told you that we know how to expand this imaginary part in partial waves with positive coefficients. Okay? So we know that these two things I can compute for small s and t at low energies. Here, s only appears here because it's a function of mt. So this is relating things that happen at low energies to an integral over high energy states. Okay? And the fact that we have positivity, we'll be able to use to actually put bounds on these coefficients. So for instance, what is the simplest bound that we can put? So the simplest bounds, they're just positivity bounds. We use the fact that the optical theorem tells us that the imaginary part of the amplitude at t equals 0 is just s times the cross-section. Okay, this is just the usual statement in your textbook. So what does that mean? You can check that if you expand this for small s and you take the forward limit, expanding this for small s means taking derivatives here on the left-hand side. So this directly tells me that any even derivative of the amplitude at 0t at low energies, so this is picking up the coefficient of s to the 2n in the forward limit in the EFT, can be written as the integral of the, oh, sorry, yeah, this is here. Thank you. Thank you. So let me write this as m. So we can see that any term like this, all of these derivatives at low energy of the amplitude, because they're a positive integral of a cross-section, they need to be positive. So what does that give us in an example? Let's do a simple example. Let's just think about a massless scalar with derivative interactions, something like a U1 Goldstein boson. So what does the amplitude look like? Something very simple, because s plus t plus u equals 0, the first has derivatives, right? So there's something like g2 s squared plus t squared plus u squared plus g3 STU plus G4 S squared plus T squared plus U squared squared plus dot, right? This thing is essentially an operator that looks like this, right? This thing is an operator that looks like this, et cetera, et cetera. Okay, so if we run through the argument, we take the forward limit that makes S equal to U, T to 0. So only the even terms survive in the forward limit. And then you pick up by taking derivatives any even term. So what we find is that G2N actually has to be strictly positive. Otherwise, it will violate unitarity, causality, all of these principles that went into this relation. Okay. Okay, so this is the first example we have that Wilson coefficients cannot take any value. Okay. Dimensional analysis maybe doesn't fix their value. I'll tell you that they are actually constrained. Okay, this is not super new. This was known from the 80s. There's a famous paper by Pham and Trong where they did this for the leading higher derivative for the Pine Lagrangian, which is something like this, but without full crossing symmetry, without like invariance. Now, these days, we can do a bit better. Using in more detail what I showed earlier. So if you expand at low energies, if you compute the difference between these two terms here, and then there's this high energy part, for this example of the scalar, you would get something like this. So you have the piece that you can compute in the EFT. So this is amplitude minus these residues in the EFT. And then you expand at low energies. It's going to go like 2 G2 minus T, G3 plus 4. Okay, so there's going to be a whole series here. And that's the part of this dispersion relation that we can compute using the effective theory. Okay? Because we're expanding at low energies for small s and t, we can just use the EFT. Okay, and the statement is that this thing will be reproduced, the imaginary part of the amplitude, which in general I will have to write in terms of partial waves, right? So there will be something like 16 pi, sum over j, some integral of the imaginary part of these AJs, which we know it's positive, right? This thing is positive. Then something that looks like this. So this is a contribution from the U channel. And then these are the general polynomials, which are known functions of S and T. So the name of the game now is that if I can find any operation I can do on the right-hand side, which gives me something positive. So I expand for small s. I pick up the right order in the expansion here. If I can find any operation that makes the right-hand side positive, then I would get a non-trivial constraint on this coefficient. Okay. Now, the simplest operation we already saw. We just take the forward limit. If we take the forward limit, then we're going to get some simple constraints. That already will let us put a coefficient. So from the forward limit, think I might have forgotten a bunch of factors. But I think here there's. So from the forward limit, I can just read off the coefficient of G2, for instance. I just set S equals 0 on the right-hand side, and I expand for small t, right? So this is just going to give me essentially a factor of 2 or something like that. All the Legendre polynomials at 1, at cosine equals 1, they're 1, right? So actually what I learned from this exercise, if you keep track of the right powers of S and the masses and all of that, did I miss something? Yes, I missed. The only thing that survives is this factor of 1 over m to the 4th. So what we find is that G2 is this. What do I mean by this bracket? I just mean the integral over all values of m, of the mass of the high energy states, the sum over all spins by these positive coefficients. Okay? So this is a positive average over whatever is in the brackets. And here tells me that G2 is just the average over 1 over the mass to the 4th of these guys. Right? Okay, so this is consistent with the expectation that this G2 coefficient, right, because the amplitude needs to be dimensionless, this is a coefficient of something that has dimension of energy to the 4th. So of course, if the first particle, if we replace the mass of each particle by the lowest one, this will be greatest, right? So this should go like 1 over m to the 4th, where m is the mass of the lowest particle, okay? But here, there's this order 1 coefficient that we cannot control. However, let's do something like that. So now, if we look at G4, so G4 means that we will need to expand this to order s squared, or to order s, to see the coefficient G4. And if we write the right-hand side, we can expand these Legendre polynomials. We know what they are. We just do the expansion. We know this. So let me just give you the answer. What you find is that this thing is 1/2 the average of 1 over m to the 8 divided by, sorry, just that. Okay. Now, okay, here I'm using dimensionful Wilson coefficients, not dimensionless Wilson coefficients. Right? So again, this thing, as we expect, would go like 1 over m to the 8. Okay? However, this is a positive average. So I can use, yes?
Maybe a stupid question, but like, how do I understand the average of the mass? Like, I don't really understand it.
The average of the mass, it's just an integral over high energies, right? So I just wrote it as a mass to use this intuition that you should think about these partial waves as the exchange of some massive higher spin particle, right? But it's just whatever is the energy of the process at above the cutoff. Yeah, right.
You're expecting in terms of integral, like what density?
Okay, let me just be super precise. This of f is 16 pi 2j plus 1 integral dm squared over m squared That's what this bracket means. So it's m squared?
M squared.
Yeah. M squared is both in the positive partial waves, and then it's the argument of whatever appears here in these functions, right? So for me, m squared was 1 over m to the 4th or 1 over m to the 8th. So I'm just saving chalk because this is very large. But literally, that is just what you get when you match the Taylor expansion in S on the left-hand side and the right-hand side, okay? There's no more mystery. I just wrote it in some some way.
We should also have G3, right?
So G3 you can get in other ways. So G3 I won't talk, but there's also a sample that gives you G3 because I can expand in small t, and there will also be a sample for G3. But yes, there are some rules for each one of the Wilson coefficients.
What makes complicated? I mean, it's not like the expansion or a T?
No, the sum rule is not complicated. It's more complicated to get a bound from it, which is what I want to do next. Yeah. Yes?
The capital M there, it's the HSU rates.
Yeah. So I was saying that if you think about this as really massive particles being exchanged, it will be this UV cutoff would be the mass of the lightest particle, which is not in the EFT. Okay, but why is this more detailed sum rule better than just saying that it's positive? This is a positive average. So actually, we can use a Cauchy-Schwarz inequality. Right? So we can say that this thing, so let me write this as 1 over m to the fourth, 1 over m to the fourth, right? And this thing should be smaller or equal than the average of each one of the, in particular, right? One of these guys, right? So I could write this as but I can write one of these ones as G2. Okay, and this one, I already told you that this basically has to be smaller than or equal than 1 over the lambda UB, right? So actually, I get an inequality that tells me that okay, so this is what I promised, right? Because I can write this in a different way. I can write this as just normalizing by the right power. So G4 lambda to the 8 UV, that's the dimensionless Wilson coefficient, to be less or divided by G2 lambda UV to the fourth. So again, this is the leading irrelevant coupling. This is 1 next. This has to be less than 1/2. And this is a sharp bound. Okay. So this ratio of Wilson coefficients can at most take that value. Yes? Yeah, previously, yes. Here, I was being lazy and I didn't divide the powers of 1 over the lambda explicitly. Yeah. But yeah, otherwise, this will have a 1 over lambda to the fourth already embedded in it, and et cetera, et cetera. Yeah. Okay, and this carries on. One can do this fully systematically, yes?
So this is okay for the rational of the amplitude, right? Are you absorbing the non-analytic terms into G2, G3, G4?
No, so that's why this assumption of weak coupling was important. What about the logs? And that's why I had to assume weak coupling. So this assumption of weak coupling means that because I'm going to add that all of these coefficients are smaller than the leading one, and then these loops that enter some rule, they will all be relevant, so they will all be suppressed by powers of this guy, G2, which means that, that I can ignore them. But of course, you can include them also, and they will provide some small correction to these inequalities. So if you wish, this is true plus order loops. Or plus order like G squared. Or I guess because I divided by G, there's only one G. Okay, so this is just a simple bound that I can get by hand. There's a fully general strategy I mentioned, which is if I can do any operation on the right-hand side that gives me something positive, I can also apply it to the left-hand side, and that will give me an inequality on these Wilson coefficients. There's a game that one can play, so we can write the sum rule. The sum rule takes the generic form generic form, let me not call it S, let me call it BEFT. So this is some function that I can compute in the effective theory, which is here the left-hand side, this thing over here. Right? So the sum rule looks like this thing, which comes from a dispersion relation, equals some B at high energies, which is also a function of S and T. And this is a function over functions with unknown but positive coefficients. So if I can find any operation, any function that when I apply it here to both sides, gives me something positive, right? So if it, for instance, if it's some function that makes, when acting on the Legendre polynomials, it's always positive, then I will have an inequality like this, and now I can read off as an inequality for my Wilson coefficients. Okay? Here I just did a simple example, which was taking the forward limit. So this f can be anything. Can be take this thing, integrate it with your favorite function, take the limit that you want, take derivatives, take the limit, and integrate whatever functional you want to apply. Then you can do. Okay? And there's a systematic way of doing this using tools called semi-definite programming. It's basically the same tools that people use when they do the conformal bootstrap, which is a very similar problem, where they have some low-lying operators equal some sum over high-energy stuff, and then they find functions which are positive in the unknown part, and then they have a bound at low energies. Okay? So this is a systematic way to bound all of these GIs over G2s. So we always have that. There's two-sided bounds that look like this. When you carry out this in practice, you always see that these coefficients are order 1, but they're actually known numbers that you can determine. So I think I'll be able to show you one plot in a second of an example of these bounds. Okay, let me say one last thing. So for the problem that we discussed the other day, this problem for gravitational scattering, there's something nice that happens that gives you an intuition of why something like this can be true. Okay. For the scalar case, it's a bit more subtle, but for the graviton case, it's pretty simple. Is that if you write this sum rule, you can see that at leading order, the simplest sum rule only involves G Newton. So this is for this amplitude that we wrote. Remember, we had this amplitude for scattering of 2 gravitons and 2 scalars. There was something like 2, 1, 3. Where these were divided by the right power of the UV cutoff. Yeah, the leading sum rule from this looks something like this. Just looks like kappa squared, which is G Newton, divided by T, equals this average. So it's basically like a sum over high G states of these partial waves with some known function here. Okay. Now, the fact that we can apply a functional to the right-hand side that is positive when acting on these parentheses, right, basically tells us that these couplings, they can only add up to G at most. Okay? So it seems that naively you could have like any strong interactions close to the cutoff, right? But at least when they couple to these states here, these interactions cannot be too strong. They have to add up at most. Okay. And that gives you an intuition of why the coefficients will be suppressed, will have an upper bound in terms of G Newton in this case, or G2 in that case, because every other sum rule just writes other Wilson coefficient in terms of the partial waves. So if I already told you that the partial waves can be at most as big as the Wilson coefficient, then it's natural that we get inequalities that look like this. Okay, so let me just show you, to end, an example of these bounds.
Show it in the middle or the sides?
In the middle. I'm not going to write more. So. One sec. This one. Oh, I think I need an adapter.
This one?
Yeah. Okay, so you can ignore this thing at the bottom, but so this is for 4 graviton scattering, not for this example that we discussed, but I also wrote this amplitude. So there was this alpha coefficient, which was the coefficient of the non-minimal 3-point interaction. Here I call it G3. So this is the coefficient of the R³ term divided by G Newton. And here is the coefficient of to the 4th operator. Again, the next correction in Einstein gravity as an effective theory, both normalized in units of the cutoff. And actually, we see that only the region inside of this blue, of this green area are allowed. Okay? If you choose this Wilson coefficient to be somewhere out here, that would be inconsistent with all of these principles that we just described. Okay? Now, there's 2 plots here because things change whether you assume that there's further light species or not. So if you only have a graviton at low energies, or if you have also other things, that's why we have 2 plots. The tighter one is when you assume that there's only gravitons. If you assume that there's other particles in the IR, then you can get this wider region. Okay? But this is just an example. Okay? We can actually do this for any coupling, essentially. So if you are interested, I can show you more later. But any coupling in this EFT, we can run this game of finding these functionals that optimize the minimum, the maximum value of the ratio of any coupling to the leading Wilson coefficient. And we can find sharp bounds on these quantities. Okay? Okay, so let me just wrap up. It turns out that at the end of the day, we can learn more than we expected from imposing these principles. Right? Naively, these principles, they're kind of taken for granted when we write a Lagrangian, when we write an EFT. Hopefully, it was useful to see how they show up directly in scattering amplitudes and how they constrain them. But I think this latest point I want to emphasize because it's something that you would completely miss if you just write a Lagrangian. Right? If you write a Lagrangian, if you just think about the Lagrangian very hard, it's very hard to argue why this coefficient should satisfy any inequalities. And it's only because by thinking about scattering and how scattering can probe these principles, these deep principles that our theories are based on, that we can actually say something very sharp about our effective theories. And for instance, why is this useful? Because if I have a sharp bound on the Wilson coefficient, and now I put a bound on this Wilson coefficient for an experiment, then I also have a sharp bound on the scale of new physics, right? I know exactly if it's a factor of 10, a factor of 2, where is the mass of the next state according to this experiment in this sector. Okay? So yeah, I think with that, I will finish. And thanks, everyone. This has been a lot of fun.
extend or to apply this like strong dualities?
Yeah, I mean, this is generic for any EFT. I don't know if maybe you're asking, the question is, can we apply these bounds to theories that have weak and strong dualities? Yeah.
We extend is in the regime where we have a weak coupling. Can we extract?
Well, maybe you would learn something about the strongly coupled phase using the duality, but I don't know how to use the duality to say something, if that's what you're asking.
Okay.
Yeah. More questions? Yes. In what? In curved space. Well, in curved space, the only thing that you would have are corrections to these coefficients, which are 1 over the order of the curvature of the space, right? So as long as the space is like large, right, then you should expect only correction. Say in like early universe or something like that, you should expect corrections that go like powers of Hubble or something like that, right? But yeah, I think the whole story should hold. In fact, in ADS, some of my collaborators have shown that you can lift this flat space bound to give bounds on effective theories in ADS, and there's a complementary approach that directly does this using holography. But yeah, this is valid for any EFT, okay? So pick your favorite EFT. You can run these sort of games. And okay, you can put your EFT then wherever you want. Yeah. Yes?
What if EFT is like a lattice action and you're adding irrelevant terms to get some desired like improvement in accuracy? You don't have Lorentz symmetry, you still have things.
That's right. So here what would fail, well, many things would fail. The question is, what if your EFT is a lattice? So yeah, definitely here I assume that I'm talking about relativistic quantum field theory, right? So if I wanted to study things like a lattice, first I would study whether these things hold, for instance, in the absence of boost symmetry, right? Whenever like we have a non-relativistic EFT, then you can ask if symmetries hold. And I think that's a simpler question before trying to go all the way to some Hamiltonian on the lattice. So yeah, I don't know if I mean, many of these principles I wouldn't know how to phrase. Okay, of course you have unitarity and these kind of things. But I also see this as something about universality, right? The whole point of effective field theory, it's more that when you're going to the continuum limit, right? Like you can tune all of these things in the UV in the lattice, right? But in the IR, you'll typically land around the same fixed point where you actually can do perturbation theory, where you can use a continuum Lagrangian, right? So this is directly going there, not trying to say something about the UV. That said, for these non-relativistic theories, in the last year or so, there's been 2 or 3 papers that try to put bounds on this. For instance, one natural place is the EFT of inflation. The EFT of inflation, you have spontaneously broken time translation symmetry and boost symmetry, right? So the analytic structure of the amplitude is more complicated because you don't have the nice properties all the nice properties that we discussed, but people have been trying to put bounds on, say, kind of the Wilson coefficients in the EFT of inflation. Yeah.
All right, I'm sure there might be more questions, but I think in the interest of time, let's stop there. Let's thank Julio one more time.